honored to have TMS's president, Dr. Cerreta from Los Alamos National Labs, next to tell us about the lab work and history.
I'll try to move it along so that you can get to the closing talk of the day by Tom. And so I know he and I have been joking back and forth all day about making sure that I left time for him. So when I was asked to do this talk, Jim Robinson, the executive director for TMS, approached me and said, I think what you want to talk about is how materials shows up in the history of Los Alamos and what materials looks like at Los Alamos National Lab today, because I'm the material science division leader at Los Alamos National Lab. And as I thought about why that might be a good topic, one of the things that sort of became apparent to me is how deeply involved Los Alamos National Lab has been, not only in TMS, but showing up for AIME. Those of you who have been around AIME for a while know that there have been a number of TMS presidents from Los Alamos National Lab: Dan Thoma, Rusty Gray, who was actually my postdoc mentor, Jim Foley, and now myself. Dan Thoma notably has also been on the board for AIME, and of course one of our previous lab directors is a highly celebrated member of TMS and been recognized by AIME many times, Dr. Siegfried Hecker, who many of you may know as the scientist that the United States sent to North Korea to evaluate whether or not North Korea was actually making plutonium. And so, and then finally, really reaching back into the archives, one of the premier metallurgists from Los Alamos, a man named Cyril Stanley Smith, has his namesake on a Pinnacle Award for TMS. And so in those ways, and probably in many others that I'm clumsily forgetting, Los Alamos' history and TMS's history, and therefore AIME's history, are deeply woven together. And so today, with sort of asking you to keep all of that in mind, I'm going to talk a bit about how material science shows up in the mission for Los Alamos National Lab. But I'm going to do that probably in a way that you're not expecting me to do. I'm not going to focus heavily on the weapons mission, only a little bit. And then I'm going to get to another aspect of our mission and how material science solved a long-standing problem. For those of you who don't know, and before I really dig into the talk, Los Alamos National Lab sits in the northern part of the great state of New Mexico, about 40 minutes north of Santa Fe, New Mexico. You drive a vertical U when you drive from Santa Fe to Los Alamos. Santa Fe sits at about 7,200 feet. Los Alamos sits at about 7,500 feet, so about 50% higher than Denver. And that is where, for many, many years, the University of California managed the laboratory. Today, we're managed by a combination of Texas A&M, Battelle, and the University of California. But because of that University of California history, we have aspects of the laboratory that look a bit like the way you would organize a university. We have chemistry and physics and biology. We have a gym and a cafeteria and a library. And then we have pieces that don't look so much like a university, like a plutonium production facility and an explosives production facility, firing sites and things like that. And for that reason, there's a tremendous amount of R&D that happens at the lab. We're about 14,000 employees right now on the Hill, about 500 postdocs, the largest postdoctoral program in the NNSA program, which is the National Nuclear Security Administration. And we cover about 49 square miles in the northern part of the state. And there's good reason for that. You don't really want to be doing much of the R&D that we're doing on top of each other. You want to have some ability to spread out. So with all of that in mind, I'll start my talk. And sort of like many of you have, I'll sort of start at the beginning. And I think most people know that Los Alamos as it stands today was really born out of sort of a worry that Einstein approached Roosevelt about, then President Roosevelt about, which was that the Germans were really getting quite organized with regard to their thought process and their R&D for building a nuclear weapon. And sort of paraphrasing the letter that Einstein wrote to Roosevelt that now hangs in in the main administration building of Los Alamos. He says, you know, the United States better get to it because the Germans are going to beat you. And so we did just that. And scientists, who I think most of us have heard of, J. Robert Oppenheimer, and a general, Leslie Groves, were sent about the business of starting a program up in Los Alamos to design the first nuclear weapon. Very, very quickly, 2 designs were agreed upon. Both were built in 27 months, which is just mind-blowing to me because I don't think we could do anything in 27 months right now. The first of which was tested in the southern part of the state in July, and that first test had a yield equivalent of about 21,000 tons of TNT equivalent. Of course, many of you know then the only 2 weapons that were dropped in a wartime action were the first weapon on August 6, 1945, which was dropped on Hiroshima. That was Little Boy, which is a 15-kiloton weapon. And then again, on August 9th in Nagasaki, the second weapon was dropped. That was a 21-kiloton weapon, Batman. Quickly thereafter, World War II came to a close, and there was some acknowledgement now that nuclear weapons were a technology that were out of the bag, and that wasn't really something that you were going to be able to shove back in the bag. Many things came out of sort of that realization, but one of the things that came out of that realization is that you probably couldn't just close the doors on Los Alamos National Lab and walk away, that you probably were going to need a lab, at least for some period of time, to understand the technology associated with nuclear weapons. And that really became the job of Norris Bradbury, who was the second laboratory director and the longest standing laboratory director for the lab for Los Alamos. He really had sort of a threefold vision for Los Alamos, and that was really that he really was under the impression that there would be a start, a middle, and an end to nuclear weapons research, and that while we weren't at the end when he was installed as laboratory director, that he was sort of going to usher it to its end. And he really wanted to design a laboratory and a project that was about doing that and stewarding that sort of start, middle, and end of R&D for nuclear weapons. He then began to really examine the size of the laboratory and what it was doing and tried to right-size it for what he thought that mission was. He also understood that the laboratory had developed quite a bit of capability and was really starting to be quite thoughtful about that capability. And so with all of that in mind, he started to really physically rebuild the laboratory, both as far as who was staffing the laboratory, which largely became a civilian operation under his tenure, and as well as rebuilding the physical structures of the laboratory. Of course, today, Los Alamos' mission is primarily to serve the nation's nuclear deterrent. Los Alamos is the design agency for over 95% of the deployed stockpile in the United States. We are also the production agency for the plutonium pits as well as the detonators within the weapons in the stockpile. And what this really means is it means that you need to have a capability both from a fundamental and an applied science understanding as well as an engineering capability that supports that for applications that really have a high demand on precision for their certification and are really going to insist on multiple safety and surety obligations. So in other words, you better be really sure that this thing's going to work when you need it, and you better be really sure that it's not going to work when you don't. And so, and that sort of changes the think on how you're going to engineer and certify both new designs as well as the materials in those designs. But our mission is really much, much broader than just weapons. When somebody asks me what we do at Los Alamos, of course, what I say is we really have a threefold mission. We have a robust capability to support the nuclear deterrent, which is really today shows up as a letter to the United States president that says, yeah, if you need these, they're gonna work. And we have a huge surveillance mission for the stockpile that supports that. But because of the capability that we have to house for that, we are able to be responsive to energy security applications as well as global security applications. And it's that middle application that I'm going to talk to you a bit about today. One of the things, though, that's sort of interesting is when I say that, I frequently get from friends and colleagues sort of wink, wink, nod, nod. That's cute that you do energy security and global security, but we know that it's mostly weapons. And what I'm going to sort of try to prove to you today is that what we do in energy security, and I won't show it for global security, but maybe if you believe me in energy security, you could extend it to global security. But what we do in energy security today really has long-standing roots, and it goes all the way back to what Norris Bradbury was thinking about when he sort of stood and looked at the lab after World War II and said, you guys have a lot of capability here, what else could we do with it? So post-war, Bradbury, as I said before, was really contemplating the laboratory's future. He was sort of sitting there with a lot of capability that had tremendous achievement. But he was, like I said, he was really of the opinion that nuclear weapons research would diminish, that there was a start, a middle, and an end to this type of work. And he was also of the belief that nuclear weapons would soon become obsolete, that they was demonstrated what they could do, and we would sort of say, well, glad that chapter's behind us, we'd put them away. And quite frankly, some of his thoughts in that space were buoyed up or shored up by a testing moratorium in 1958. So he became sort of confident in his thought process there. As he was thinking about that, though, he was, and really, again, thinking through what Los Alamos could do, he started to think through where else nuclear power, nuclear materials, and the ability to do that kind of research could show up in application to support the United States. And one of the things you start to see on this slide is sort of a long list of places where Los Alamos started to stick its nose in and say, let's do some meaningful research with regard to the development of nuclear technologies for things like nuclear fission research, industrial applications of nuclear explosives, health physics research. Of course, there was a tremendous amount of high energy density physics research and subatomic exploration. But the one that I'm going to talk about today is how Los Alamos really became involved in space exploration, and particularly the design of microreactors for nuclear thermal propulsion. And that sort of shows up in its earliest history as Project Rover. Then and today, one of the things that became pretty obvious was to support all of this mission space that Los Alamos was going to have a very large material science program. And the capability at Los Alamos for material science is much broader than the division that I lead, and shows up in a number of divisions, both as primary divisions leading material science as well as divisions that dabble in it. And I'll talk about that a bit, but the primary goal of material science at Los Alamos is to develop materials with tailored performance or controlled functionality, and then be able to predict the performance of those materials. As I was sort of joking about a few minutes ago, one of the things that happens at Los Alamos is that we don't get to test our final product, and so we have to be able to predict the way in which it's going to perform. We don't do that across all areas of material science. We do that across 7 areas where we believe we need to be leaders, and those areas are shown in orange across the bottom of this slide. Many of them are probably not terribly surprising to those of you who know the lab. We have to have excellence in actinide research, of course in energetics, in materials under dynamic loading conditions, materials in harsh environments, because what we do really well at Los Alamos is make a material and then do horrible things to it. And more and more, we need a capability in manufacturing science. For university faculty in the audience, you should hear we really need students in that area. And then we have some capability in things that may not seem like typical areas of research that Los Alamos might engage in. And those are areas like integrated nano and complex functional materials. I'm not going to dig into that, but there are sort of hidden ties to why we do those things and how they show up in our energy security and global security missions, maybe more formally than they do in the weapons security mission. To cover the gamut of that materials capability, we have over 1,000 employees at Los Alamos doing, where their day job is primarily on materials R&D, both from an applied and fundamental standpoint. That is sort of a $300 million R&D budget if you don't include the production agency budget at Los Alamos. And that's at a laboratory that this year crossed the $4 billion mark. We have a sort of a large range of facilities for material synthesis, testing, characterization, and of course, small-scale characterization of properties and rather large-scale characterization of properties. To give you sort of an idea, we have the ability to detonate up to 2,000 pounds of explosives on the Hill, and so that definitely does rattle the windows in Santa Fe. We have a fairly nice set of user facilities at Los Alamos, and so those are facilities that anybody in the world can write a proposal to and get time at. They're facilities operated by the Office of Science. That's the Center for Integrated Nanotechnologies is one of those. We also have the National High Field Magnetic Lab, which is an NSF-funded user facility, and we have 2 NNSA-funded user facilities in DART and the LANS Accelerator, which are both facilities that allow you to examine dynamic experiments with very with high temporal resolution. We're working on spatial resolution. It's certainly not the spatial resolution of a facility like the APS. And where we don't have facilities, of course, we partner. We partner with our sister NNSA labs as well as facilities around the world. When you start to look at the end states for that materials capability, we start to have goals associated with lots of those areas of leadership I showed in orange across the bottom of the slide a few minutes ago. And what you'll see is, as I promised, not all of those end states are dedicated to the weapons program. And in fact, the red ones are the ones I highlighted as not being dedicated to the weapons program. And I'd like you to sort of focus on the first one. The first one that's in red is the one to deploy nuclear fuel or cladding material in an advanced reactor in less than 10 years. And a lot of times when I have folks show up at Los Alamos and ask why in the world would that be one of your end states, I have to remind them of the history that I'm going to share with you right now. So getting back to Bradbury and when he was thinking about laboratory diversification and what else we could do with the capability we had in the Hill in the early mid-1950s, at that same time, coincidentally, a gentleman named John von Neumann visited Los Alamos, and he was really interested in exploring technology associated with nuclear rockets. He had been part of an advisory panel that included the head of the Los Alamos reactor program, and very quickly thereafter, Los Alamos, which was known as the Scientific Laboratory, or LASL at that time, and Livermore were directed by that advisory panel and therefore the US government to start exploring feasibility concepts for nuclear rockets. At Los Alamos, that showed up as being organized in a division called N Division, and the first division leader for that was a gentleman by the name of Raymer Shriver, and his real job was to perfect an ICBM, an intercontinental ballistic missile, that had an NTP, a nuclear thermal propulsion capability associated with it. Of course, the first generations of that reactor design for an ICBM were not flight-worthy. They were deliberately prototypes that were designed to just examine whether or not you can meet the requirements for something that associated with an ICBM. And the first prototype was something that was referred to as Old Black Joe. I promised lots of other colorful names through the parts of this talk. But that was really a 1,500 megawatt reactor that was graphite ammonia cooled reactor design. What then sort of happened almost immediately after showing that All Black Joe was sort of a feasible technology and might be something interesting to take a look at, it became clear as far as the US government was concerned that we really weren't going to be using a nuclear thermal propulsion for nuclear weapons and specifically for ICBMs. And so what the entire NTP program was redirected toward was space exploration and space technology. And consequently, the program was defunded to some extent, and the division of labor between Livermore and Los Alamos was examined, and the program at Livermore was moved to Los Alamos, and that program became known as Project Rover. And the entirety of Project Rover was transitioned to NASA because it was going to be a space exploration program with the reactor concept staying at Los Alamos. And at that time, NASA had sort of done the analysis and decided that what they really needed was a 1,000 megawatt reactor for what they were going to need, what they were going to do in terms of space exploration in orbit of the Earth and in orbit of the Moon. And the initial prototypes for this were going to be reactors that, just like Old Black Joe, weren't going to fly. And so they were dubbed KIWI, birds that don't fly. The first design was KIWI-A. It was one that was really based on that Old Black Joe design and was somewhat less powerful. But one of the things that that this relatively simple concept was able to do was sort of feed the scientists questions and answers with regard to how you would design the bigger or scaled up prototype, which was going to become KIWI-B. Of course, what you probably all recognize about Los Alamos is we don't test our nuclear devices on the campus of Los Alamos. We do that elsewhere, and most of that work is done in Nevada today. And so nuclear rockets and their reactors were also tested in Nevada at like I promised you, another colorful name, Jackass Flats, in Area 25. That facility had a nuclear rocket development station and a reactor maintenance assembly and disassembly facility. All the reactors I'll be talking about in this talk were tested there at that site. So KIWI-A was the first reactor tested there. It the first test was, or full-scale test was in 1959. It was viewed as a success at the time, but one of the things that was pretty evident was that the materials that were available for this reactor were not going to make it in terms of how long these reactors had to perform. There was quite a bit of hydrogen damage to the graphite components within the reactor, and there were a number of corrosion and erosion issues with regard to the reactor. KIWI-A was a simple prototype. It was, like I said, going to be used to motivate KIWI-B, which was going to be 10 times more powerful. And so they really needed to understand these corrosion and erosion problems. But quickly thereafter, after 1959, some of the interest in nuclear rockets and even space exploration became a little bit tricky to navigate. The program itself really didn't know how to solve the technical challenges associated with KIWI-A. They were playing with a lot of different designs and technologies, but they weren't having success. And while it was part of the 1960 presidential platform to talk about space exploration and particularly missions to the moon, there just was a little bit of molasses in the system with regard to really getting the funding this project needed and getting it in a place where it had a mission space that was really being supported nationally. However, as they continued to sort through it, one of the things they found was that largely most of the problems with KIWI-A were problems that could be solved with material science. The first thing that they did is they went and they found a way in which to coat the graphite components within the reactor. They coated them with niobium carbide, and this provided sort of an effective shield that protected the graphite from the hydrogen. They were also able then to vapor deposit niobium pentachloride to protect the graphite, but the problem then was that the chloride in that coating was damaging the uranium fuel, and so they needed to protect the uranium fuel. They started to examine ways in which to do that and coated what was then uranium carbide fuel with a pyrolytic graphite coating. And this really then became the basis of the fuel elements for the microreactors coming out of Los Alamos. All of these technologies together really started to solve the corrosion problems they were seeing in the reactors and led really to the KIWI-B design, which was that much bigger reactor. And it really was quite successful in protecting against vibration and corrosion issues, and they could really run the reactor for quite a bit longer than KIWI-A ran, and were seeing very minimal corrosion within the reactor. They tested sort of the first prototype of KIWI-B in 1963, and they were still seeing a bit of a vibration issue in that design. Having sort of done what they could with materials, there was a little bit of a redesign of mounts and things like that within the reactor, and KIWI-B, B4B, was tested, and that was viewed as successful. In August of 1963, KIWI-B4E ran for 8 minutes at 900 megawatts. And this really became the basis of what Los Alamos does in microreactors and nuclear thermal propulsion technology today. So based upon that success, that sort of launched a new program which was called NERVA. That was the nuclear engine for rocket vehicle application. And it was hoped early on that the NERVA program would be flight testing a reactor by 1967. However, the landscape changed a bit nationally. There were rising costs associated with the Vietnam War with regard to the Great Society, and there was sort of mounting competition from the Apollo program and with regard to this reactor design and draining resources. And so it was sort of a bad time for the Rover project not to have a distinct mission. It was decided at that point to set aside the NERVA program, but it didn't stop microreactor design, and NASA and Los Alamos kept working on designs to explore microreactor technologies that could take payloads beyond the moon, and that was the first vintage of that design was really Phoebus, and that series of reactors were sort of the largest of the microreactor series at about 5,000 megawatts. And then in the late 60s, they went the other direction and started to examine sort of a smaller set that would be for Earth orbit and missions to the moon, and that was the KIWI series. And again, those were all based really on what was learned from the KIWI series I was talking about before. And one of the successes of the KIWI series is they really got to a point where they had a reactor that they thought could be fielded on the Saturn V as one of the upper stages of the Saturn V rocket. So they were really looking and trying to push this as a technology for a mission to the moon. And that was really great, except in July of 1969, we landed on the moon without nuclear thermal propulsion. And that became a huge success story, and sort of the interest in nuclear thermal propulsion on the Saturn V waned. And so even though the prototypes, which were never flight tested, all worked, they had lacked really a specific mission or application since 1964. At the same time, the Kennedy administration was really starting to fear a costly space race with the Soviets. There was some consideration of where this reactor technology would show up with regard to missions beyond the moon, and a manned mission to Mars was, of course, considered. But that mission was dropped because of mounting concerns of costs happening within the public sector. And ultimately, the Rover set of reactors that KIWI, Phoebus, and KIWI series were never flight tested. And in 1973, this program was canceled was announced at Los Alamos Scientific Laboratory. With that said, though, I think you could take away, well, so why is Los Alamos still in the business of this if they canceled this whole thing? There were a lot of achievements of the Rover project. There were some knock-on technologies from the Rover project that were ultimately adapted by the Saturn projects at NASA. Notably, if you look at items 2 and 4 within Los Alamos, there was a lot of technology developed around materials processing, particularly nuclear fuel processing, cladding and coatings, and how to implement them in a harsh environment of a reactor and get them to work. There were real successes in the design space for microreactor technologies, and notably something that I don't personally play in or my division personally plays in, but is really a successful part of Los Alamos' engineering program, as modern heat pipe design is really something that was sort of authored at Los Alamos and has long-standing expertise at Los Alamos. So today at Los Alamos, that really shows up in a number of ways. In 2018, we had a kilopower reactor using Stirling technology demonstrated at NSERC. NSERC is the National Criticality Experimental Research Center out in Nevada. We still are testing our reactors in Nevada. And again, that was a design that was largely enabled not only by standing on the shoulders of those who had designed microreactors in the past, but also some of those materials capabilities that I was speaking about that enabled KIWI-A and others. Even though we are in an NSA lab and Idaho National Lab is the nuclear energy laboratory, Los Alamos is the home to nuclear energy advanced modeling and simulation for DOE-NE, and we have the national technical director seated at Los Alamos. We have a facility for nuclear fuels research that sits within my division, and we just got congressional approval for a pilot scale nuclear fuels facility across the street. So we're able to go from sort of little bits of nuclear fuel to hundreds of kilograms of fuel here in the next 2 years. And that facility is called the Low Enriched Fuels Fabrication Facility, and that'll sit down near TA-55. If you haven't heard of TA-55, that's where our plutonium production facility is. We have, as I mentioned, we maintain leadership in heat pipe design for reactors. And today we have sort of long-standing and new partnerships with NASA, Westinghouse, Kairos, TerraPower, and really looking forward to supporting DOE in their strategy with regard to advanced reactor demos. So with all that said, I'll stop talking and take any questions, but I do want to give credit to the people who really were smart enough to help me with these slides, because those of you who know me know this is not where my technical depth is. But as you sort of take in the list of the people who were smart enough to help me with this, I want to point out a long-standing materials person on that list, Paul Dunn, who is also a graduate of Colorado School of Mines, so a little bit of a nod to AIST and the steel folks, because Paul most certainly got his background in steel. Thank you.
Ellen, any questions? Yeah. Kevin.
Ellen, question. Speaking from the steel industry, but more broadly from the materials industry, face the immediate challenge of sustainability and decarbonizing manufacturing. What I just heard today is a potential solution for safe, effective, and plentiful green nuclear power to help all of us in manufacturing in the future. My question is, from your view, how long do you feel it's going to take to get some of this green power safely on the grid in the United States?
So certainly with these microreactors, those things are being pitched all the time for their use and specifically what you're saying is, could I drop in a microreactor and power an industrial park that really's got a manufacturing technology? And you can imagine sort of the pictures that do well in sort of a layman's terms of I can replace this field of solar panels with something that fits on the back of a flatbed truck and power everything, and when you're done with it, we'll just haul it back off, right? I don't know the answer to your question with regard to how far away we are from getting that through the NRC and actually deployed. I will tell you that we're really very, very happy that one of the first new designs in that space just got approved by the NRC, and it's the first one in many, many years. And that was using some of the modeling capability from Los Alamos and Idaho National Lab to make the NRC feel good about that design. I think that and probably many of you would know better than me, there are probably likely some social and political implications before we're ready to deploy those kinds of technologies in a meaningful and useful way.
This makes me very excited about opportunity to decarbonize manufacturing and to leverage our national laboratories and the geniuses there and to convince, I don't care what political fashion, but to convince the people and to convince the government that this is safe, green power for the future.
My sense is that, and why Los Alamos gets to play in it, is that there are implications clearly for space and the DoD. And those will be places where this will get proven out before it gets used in for civilian use.
Thank you.
Okay. Bob, I think you had your hand up. Yeah.
Just sort of a tongue-in-cheek question. Will Elon Musk and SpaceX ever be allowed to commercialize this nuclear propulsion technology?
So I don't see any reason why not, right? I mean, Los Alamos serves at the behest of the taxpayers, right? And so, but it won't be only Elon Musk, right? Because you, the taxpayers, own the technology, so.
Yeah. Come out.
So there were a couple of announcements recently on magnetic fusion. Are you involved in some research?
So there's a lot of stuff going on in fusion energy sciences right now, and Los Alamos is actively involved in trying to understand what they could do at the end of their accelerator to address some of the needs of fusion energy sciences. I'll tell you, I'm probably not exactly the right person to ask, except for the fact that we've been asked to think about some of the real materials needs in fusion energy. Some of the, in fact, somebody at lunch, and I forget who it was asking me about some of the really harsh environments you would see in a fusion energy reactor, and how you develop materials that can withstand that, because you're sort of throwing it all at a material at the same time: radiation, temperature, corrosion, and so we've been involved in thinking about some of the novel alloys that could be designed to withstand those environments. And what we're looking at quite a bit is alloys that have a lot of interfaces in them, or are somewhat disordered so that they can absorb the defects within the material.
Okay, Ron.
Maybe a philosophical question, but to touch on Kevin's point about the use of nuclear energy for manufacturing. What would be your elevator pitch to try to tout to, say, Washington people about why nuclear can be construed as green, why it can be construed as renewable? Because as you probably know, there's a lot going on in solar and wind, and now in our industry in particular, green hydrogen and creating green electricity. What's your pitch for nuclear, for the back of that pickup truck, micro solution?
So I am certainly not the smartest person in the room on this pitch, but the limited parts that I've been able to see, and this is again with my materials hat on and not so much with an energy generators hat on, is that a couple things is that a lot of the technologies associated with nuclear energy are technologies where we do actually know how to recycle parts, how to reuse things. There are technologies with regard to even recycling fuel so that you can reuse it and not have to bury it back underground. We know how to certify those materials for those high consequence, harsh environments. One of the things I'm starting to see with regard to technologies with regard to hydrogen is it's very, very exciting, and I was trained as a material scientist to develop materials for new sets of requirements. Let me at it. But the problem is there aren't a set of requirements, right? There is no ASTM standard for the pipeline that pushes hydrogen through it. And so that means we're really far ways from certifying those kinds of things. Additionally, there are problems with regard to storage of that hydrogen, how we're going to do that effectively. Of course, there are lots of ideas out there, but that's going to be a huge problem. And we sort of already know how to do this for nuclear. And I think with regard to that and with regard to some of these ideas where you could drop in a reactor in a very small place where you don't have something that looks like Indian Point in New York or Shoreham out on the end of Long Island, you start to maybe relax some of the concerns of I get this structure that's here for 60 years and I'm stuck with it, right? You could drop in something very temporarily and then pull it back out. And I think that's the hope of these microreactor programs. But that being said, you should know I have solar panels on my house. So
I have a question.
Okay.
So Ellen, over time, how much has changed at the lab to go from practical experimentation to computer-based modeling? And what is the future of that area?
So I see experiments are expensive, right? And I'm an experimentalist, so I like experiments. But I see as computer models get better, as the computers get faster, and as new techniques like machine learning and AI allow us to draw meaningful conclusions with less data, there is increasing pressure for what I would call model-driven experiments, right? Not just to go out and fill out the sort of the matrix of all the different experimental conditions and have all the different robust data sets that I'm sort of comfortable with. There's sort of an increased attention on what is the minimum number of experiments we need to develop a model and validate it. And that is definitely at the heart of Los Alamos's manufacturing science mission and really drives the way in which we're thinking about manufacturing at Los Alamos. Does that sort of answer your question?
Great. Well, thank you, Ellen.
Thank you.